So in this video, we're going to talk about implicit differentiation and use it to prove a geometric identity. So the problem that we're going to solve is we're going to show using implicit differentiation that any tangent line at a point P to any circle with center O is perpendicular to the radius OP. So the first step we're going to do is we're going to identify the variables and find an equation that expresses their relationship. So here's our graph. We have our circle O, radius R, our tangent line L, and a point P that is on the circle and is on our tangent line. What we need to show is that they are perpendicular to each other, which, as we know, it means that the product of the slopes is need to be equal to -1. So this is the equation that expresses the relationship between these two lines. So our variables are slope of the radius and the slope of the tangent line. So if we look at our graph again, we can call O HK because we don't know exactly where it is, and we can call P X1 y1 because it's on the circle, and that will help us to find the slope of the radius. So the slope of the radius is the ratio between the point P and point O. You can see it on the graph. If we draw the rise over run, we can see that our rise is y1 minus k, and the run is x1 minus h. So this is the slope of our radius. For the slope of our tangent line, we know that the slope of the tangent line is equal to the derivative of the circle at a certain point. In our case, the point is P. So what we need to do is we need to take the equation of a circle, which is x minus a squared plus y minus k squared equal to r squared. We need to take that, and then we need to take the derivative on both sides of the equation. And we will do that in step 2 using implicit differentiation. So here is our equation again that we need to solve, but just before we start doing that, I just want to make sure we all remember that r is a constant in our case. So it means that the derivative on the right side is going to be 0 since r is a constant, and y is a function of x. So we will have to use chain rule to find the derivative of y. So if we go ahead, the first thing we can do is we can distribute d over dx between these two terms on the left. So we will have d dx x minus a squared plus d dx y minus k squared equal to 0. As we said, the derivative of r is just 0. We're going to use the chain rule to find the derivative of the first term on the left, so it's going to be 2 times x minus h to the power of 1 times 1, which is the derivative of x. And here we're actually going to use the chain rule twice for the entire term and also for y, because as we said, y is a function of x. So this will be 2 times y minus k to the power of 1 times the derivative of y, which is dy dx. And we want to solve to that derivative because this is the derivative of the equation. So if we isolate that, we will get minus 2 times x minus h over 2y minus k. And we can cancel out the 2, and if we plug in our point p x1 y1, because we want to find the slope at this point particularly, then this is what we're going to get. And so our final step is that we need to take the variables that we found, the slope of the radius and the slope of the tangent line, and we need to put it in our original equation. So original equation, if you remember, is the product of the slopes of the radius and the tangent line, and we need to show it's equal to -1. So here's the slope of the radius that we found, the slope of the tangent line that we found, and here is the product. So as we can see, we can cancel out these factors, and because there is a minus sign here, we're going to get -1 is equal to -1. So we have proven that any tangent line to a circle at a certain point is is perpendicular to the radius of that circle. So if you want to know why this is important, here are some few examples from real life situations where we can see a tangent line and a circle.